All right. So, ladies and gentlemen, let's take a look at this capture question. Are these capture questions? I guess it's plural. Which of the planets will have the shortest orbital period? What did you say? Was it? Oh. Can I ask a question first? Maybe a question that needs to be answered before we can answer the capture question itself. What is orbital period? Okay, so let's write that down. So if you did not know that or you don't have that written down somewhere, let's write that down right now. Orbital period means the time it takes for, I heard you guys saying something. For what? To go around the sun. Yeah, for the planet to go around the sun. You can also talk about orbital periods in terms of like our sun going around the center of the Milky Way galaxy, for example. So it's not just these. You can also talk about it in terms of the time it takes for the moon to go around the Earth, right? So all of those things have orbital period. But in this case, we're really talking about the orbital period of the planets. What is the Earth's orbital period? 365 point something days. Yeah, it's about 365 and a quarter days. So just a note there to kind of give you some perspective. The Earth has an orbital period of 365. It's something like 25 days. I don't know, something like that. Okay. 365 days is what? 1 year. So we define our year as the amount of time it takes for us to go around the sun. Which of the planets is going to have the shortest orbital period? Is it us? Mercury. Why Mercury? Because it's the closest. Indeed. So I'm going to put a little space in there if I can. Yeah, and we're going to say that Mercury will have the shortest orbital period. Okay. The shortest orbital period. And Elena, you said that it is because why?
It has a shorter distance to cover.
Shorter distance to cover. Right? Do all of the planets move at the same speed as they go around? I have another question, a follow-up question to that. Does one planet travel the same speed the entire time around as it goes around? It doesn't. Kepler's second law says that it's going to go faster when it goes where on it? Closer or further away? One of the two. Closer, further away, closer, further away. Yeah, something like that. We'll figure it out in just a second. Okay. Shorter distance to cover, and it's just the radius is a lot closer. Is that cool? Is that okay? I was going to pull up and see if I could find, where did my mind here? Hold on. I wanted to check this real quick because I think, this little chart. Do you remember we were looking at this chart yesterday? This, not only does it have the eccentricity, that was how squishy or not squishy the ellipse was. It also has the period. They call it the revolutions. The reason I know that is because if I look here on Earth, it says 365.256. Now we know. Now, I don't mean that like I'm proving you wrong. I'm saying now you know. So now you can throw that out there at parties and people will be very impressed with you, right? Okay. So if we look at how long does it take Mercury to go around the Earth, or around the sun? Around the sun. 87, 88 days, right? That means you have a birthday that much more often. Or you get older that faster, depending on which way you want to look at that. How long does it take Neptune to go around the sun? Look at that. It's really, really far away. It's 30 times further out. This 30 right here it's the distance from the Earth to the sun. They call them astronomical units, and we're 1 astronomical unit from the sun. Neptune is 30 times further out. So you walk from the sun to the Earth, and then you do that 30 more times. That's a long way, right? That's a long way. And you only have a birthday how often? 165 years. Talk about a way to stay young, I guess, huh? Again, it depends on the way you look at it, right? I want more birthdays, or I want to stay, depends on which side of that you're on. But are you with me there? If you look at these, they keep getting bigger and bigger and bigger and bigger. This one only says 11, and that one says 600. Why is that? Does that make sense?
And it switched to units.
Oh, because it switched units, didn't it? So Mars's year is it's about twice as long as Earth's. So it takes twice as long for the Earth to go around, or as for Mars to go around than Earth does. Jupiter takes 11 years for every orbit. It's kind of a long time. It's kind of interesting. So there you go. Piece of information for you today. Hey, what's wrong with the picture?
Two ellipses.
Two ellipses.
Is it that are there
I mean,
all the same shape?
Yeah, I mean, there are a lot of issues that I have with this, but the big one that I had because I pulled this out, this is exactly from your pink sheet that you did, and I was looking at it, I was like, oh, it makes me kind of cranky because all of those paths look really, really. Do you remember what the E word is? Oh, well, ellipses. Yeah, ellipses. That's what you really wanted to say, right? Yeah, eccentric, right? The eccentricity of those things is really, really exaggerated. Remember, Earth, this path here is very close. You remember we figured it out yesterday using that math website? That's supposed to be a circle. That does not look like a circle to me. Maybe it's like really tipped. You know what I'm talking about? Like if you look at a circle from the side, like if I'm looking at my teacup, right? If I look from above, it's a circle. If I look from the side, it looks more like an ellipse. So maybe that's what they were doing. Or they're just looking at all from the side. That could be. But when you draw the solar system, you will not draw it with that much eccentricity, will you? No, ma'am. Nope. Because it's almost a circle. Anything else that you saw wrong with this picture? Good, I'm glad. I wondered if some of you were going to get mad because it only went out to Saturn.
Yeah.
Uranus and Neptune aren't in there. Why would a picture of the solar system on a sheet for Kepler's laws not have Uranus and Neptune?
We didn't know that.
We didn't know they were there, did we? We hadn't seen them yet. We can see Jupiter and Saturn with our naked eye. So Brahe saw them even, right? Brahe went out on those every night when he went out and he was looking up, and he could chart the path of Jupiter, chart the path of Saturn. That's how Kepler figured it out, you guys. He looked at those and he's like, hey, that doesn't make sense. If I chart that out, it does not look like a circle. That doesn't make any sense. That's where the ellipse business came from. All right. Questions on these questions? Okay. I would like for you to pull out your Kepler's Law pages, your green and pink sheets, as well as your As the World Turns sheet. That's the one that has the 4 scientists on the front, and then it starts with Kepler on the back. Does that make sense? So you should have 3 pieces of paper out in front of you. All of them are different colors, green, pink, and brown. I just want to make sure that we've taken enough time to really think through this and we know where we're at. Because remember, what are we doing first thing tomorrow? Taking a quiz. And what's it over? All this stuff, right? Kepler's laws are on it. So this is your opportunity to learn it if you didn't before, right? This is it right here. So we looked at this one yesterday, Kepler's law of ellipses. It says that planets orbit around the sun in an elliptical shape, with the center of the sun being located at one focus. On your brown sheet on the back, if you have not yet written something down, we're going to double check that right now. If you have written something down, let's make sure that we agree on what it is. Okay? Kepler's law number 1 is that all orbits are elliptical. If you wrote something else down, like you wrote law of ellipses, that's fine, as long as you know what that means, okay? Just writing down law of ellipses may not mean anything to you, though. The thing that you really need to know is that all orbits are elliptical. And the other little piece of that is, where is the sun in that ellipse?
How do you say it?
At one of the at a focus. Yeah, it's foci or foci. I've heard it both ways from people that I know and trust. You know what I'm saying? Like when you hear multiple people say, you're like, yeah. Foci, I think, is what I like to say more. But yeah. So we're going to say that the sun at one focus. There are two foci, okay, on an ellipse. Remember, for our orbit, it's almost a circle, just barely not a circle, okay? We were going to do the math for that, and I forgot. We'll do that one of these days. I'm going to flip back to the Kepler's law sheet. We went through this one yesterday, I think, at the very beginning of our day together. Kepler's second law, we did not spend any time talking about, so I just want to make sure that it makes sense to you. So you looked at this picture. It's very strange, ladies and gentlemen, that it takes 31 days to go this distance, and it takes 31 days to go this distance. This has a lot more distance, right? Speed is distance over time. This one has a lot more distance. This one has a lot less distance. Where are we going faster? Closer to the sun? Like A to B? Yeah. Does that make sense? We go really fast when we're closer to the thing that's pulling on us than we do when we're further away. That's the big deal. Okay? And I think that, let's see here. So we look at the width. Yeah. We really want to know. Let's see. What did you say for the answer to question 7? Take a look on this is on the back of your green sheet. Question 7, which section shows a planet traveling the shorter distance? What did we say? A to B or D to C? D to C. Okay. What does that mean about the planet when it's closer to the sun? You said this already, but I just want to make sure that it's really making sense, that it moves faster, right? That would be a very valid thing for, somebody to ask about tomorrow on, say, a quiz or something. So I want to make sure that it makes sense. Wink, wink, nudge, nudge. Get it? Yeah, it's something to pay attention to. So let's write down Kepler's second law on our brown sheet as well. Kepler's law on our up here says a line connecting a planet to the sun will sweep out equal areas in equal amounts of time. That's fine. What does that really mean for us? It means, what's that? Yes, it means that the little, like the pie piece is going to be the same size, right? So if instead of making a circular pizza, you made an elliptical pizza, I think you all should go try and do that someday, right? It's kind of fun. Make an elliptical pizza, and then if you cut out slices of pizza that are all the same size, all the same area, okay, they will not all have the same path or the same amount of crust. Does that make sense? Are you with me? That's one way to think about it. And so the ones that are closer to one end are going to be really fat. And the ones that are down the other end are going to be really skinny pieces. But they take the same amount of time to get through one as they do through the other. The result of that is that a planet moves faster when it is closer to the sun. Okay? That is the big result. Okay? we can say equal area, or I'm going to say size of pizza. Does that make sense? Does that help you to kind of imagine it? The slice of pizza, size of the slice. Okay. Area in equal time. Okay. So the size of the slice means a different amount of crust. Maybe that'll help you kind of like conceptualize what's going on there. Questions on that one? Not so much. Okay. And number 3. This was the one that you did with the swinging the ball over your head. Now, there were a couple of people, at least one person that was gone yesterday. So I want you, we're not going to redo the lab, but I want you to relive it. Who can start with the description of this lab? What did you do? Can somebody start describing for us all what we did in this third experiment? David, you look like you're ready to act it out. Can you sit up and tell us the story also?
On the wall.
Tell me more.
Counted about it. We counted how many rotations in 10 seconds.
Did you hear or understand any of what he just said? Okay, sit up. We're working on communication. Sit up all the way. Colin's going to help you out in a minute, but I want you to start it out. Okay, so David, I asked you to go over and you got a meter stick and you got a stopwatch and you got some papers and you got what else?
Ball on a string.
A ball on a string. Okay. Now, Hayden, what did you do with that ball on a string? Spun it around her head. Woo! Acting like, it's like a lasso or something. I don't know. Or a ball on a string. In physics, we get to do this too. And we do this in a very much more careful way. So, if you enjoy swinging things over your head, sign up for physics. We'll do it a lot. So you swing it around your head. So you swing it around your head. How long did you swing it around your head for, Sydney?
10 seconds.
10 seconds. And Alexander, what did you do while somebody was timing those 10 seconds? Oh, she wasn't here, so you're learning right now. You're like, tell me, Miss Carbling, I want to know. All right, so somebody's got to tell her. So we swing the ball around her head for 10 seconds. And Lauren, what did we do with that? What did we do while the 10 seconds were happening? We counted the number of times it went around. Is that what you said?
Yeah.
Sweet. All right, so we counted the number of times it went around. Woo, 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 woo. It was a good time. Now, after you did that, so your time was 10 and your revolutions was some number. Okay, was that the end of the game? No, that was only halfway there. Livy, what did you do next?
Then you found the orbital period by dividing your time by revolutions.
Time by revolutions. So how often did it go around in 10 seconds, right? Or vice versa, I guess. Yeah. So we found the orbital period. Okay. And then what did we do, Constance? What was the next thing?
And we made the rope half of the length it was the first time, and we repeated the process.
Okay. So if it was fun the first time, it's going to be even more fun the second time, right? The second time, the rope was a little shorter. Okay? And when the rope was a little shorter, can you pass it back to my friend back there? Did that change the number of revolutions?
Yeah.
What happened to the number of revolutions? It went up?
Yes.
Did everybody get that it went up? Yeah? Okay, good, good. There are ways that one can get it so that it doesn't, so I wanted to make sure. So I'm just going to make a note here that as the rope length went down, the number of revolutions went up. And what, if the number of revolutions goes up, what happens to the orbital period? It goes down. It's not really an equation. It's more of a let's just make observations about what's happening. So not so much an equation as a kind of process of understanding. Okay. So as the radius, which is the rope length, the distance from the sun, it's like your hand is the sun and the tennis ball is the planet, right? As the rope length decreased, the period went down. Well, that's interesting. Question 11 said, what is the relationship between the distance and the orbital period? And you said, what? What did you say for question 11? What did you say, Jody?
I said the shorter the distance, the more revolutions you have.
The shorter the distance, the more revolutions. Absolutely, yes. And what about the time it takes to make one revolution? What's that? What? I'm trying to answer this question. What happened to the amount of time it took as the rope length goes down? What happens to the time, friends? It goes down. This is the science. This is science right here.
I love science.
I know you do. That's why I want to make sure that you're understanding it. This is it right here. This is the big money question right there. Okay? Rope length goes down, period goes down. That is it. Make sure that's written down there. Use your knowledge. Longest orbital period was what? What'd you say here? Saturn? Because Saturn has the what? Most distance. Yeah. So as you go out, longer period. Hey, look. That's Kepler's third law. Let's write it down. Number 3, if you don't have it written down already. Okay? The nice, easy way to think about it, the way that it's written down in here and the way that Kepler actually articulated it, it's a little more complicated. The orbital period of a planet squared is proportional to the semi-major axis cubed. Whatever that means, right? I mean, I know what it means, but we don't really care that much. The thing we really, really care about, ladies and gentlemen, is, okay, as the radius, or let's say the larger radius equals longer orbital period. Yeah? Did you guys write anything down for Kepler's evidence?
Stone Brahe's data.
That's right. Stolen data. Right? That's really what it was. The evidence that Kepler had, I mean, it was good evidence. It was good evidence that came from a legitimate source. Just maybe, it's kind of like laundered data, I guess, is really what it is, right? Okay? The evidence was from Brahe's data. All right. How are we doing? Got it? 1, 2, 3. We know the evidence. You know what geocentric and heliocentric are, yes? Okay. So tomorrow morning, first thing, it's going to be easy peasy lemon squeezy, right? You're going to be on like this sugar coma from last night. Or the night before. Tonight is what I'm talking about. Okay? But you're going to be able to answer those 5 questions with no problem. True? Awesome. All right. So David and Liz, I'm going to have you guys hand these out. This is more than you need. Give one of those to everybody.
You think I want to realize? So